Welcome to our continuing series of homework discussions from the Titelbaum book. I hope you're having a good day so far, and this will allow you, this one is going to be in two parts because chapter 6, the homework, it seemed to me that every problem got longer than the next one. And by the time we get to some of the last ones, the explanations are going to be rather extensive. So I think we will go up through about 6.7 for this first part one homework discussion. It's problem 6.3 that we're supposed to skip. So I'll make sure to skip that one and it'll be on the take home. Let's begin though with 6.1. So 6.1 and 6.2 will give us some relevant background for how to think about solving the 6.3 problem. But 6.1 says, let's assume special consequence and converse consequence. And both of them have to do with 4 items, some evidence, 2 hypotheses, H and H prime, and background information, K. So the antecedent of converse says, if E confirms H, relative to K, and H prime and K models H. This is a synonym for entails. This is our symbol for models. So we've got E confirms H and H prime and K models H. So we get an entailment from H prime to H given this background information. Then E confirms H prime as well. You can see why it's called converse consequence. The original consequence conditional was if E confirms H and H entails H prime, then E confirms H prime. But this is where H prime is stronger than H. So E is supposed to confirm H prime as well. And when you hear that description, you ought to be suspicious. You ought to think, oh, that's not likely to work, is it? And it's true. That's going to get you in trouble if you have converse consequence. Special consequence condition says if E, H prime, and K have this feature, E confirms H, and H and K models H prime, then E confirms H prime as well. So notice when you put the two together, you can go back and forth from H to H prime, depending on which one entails the other. So we're supposed to show that under these assumptions, if you put both of them together and you've got some piece of evidence that confirms a hypothesis, then it's also going to confirm absolutely anything you might want to pick, which is absurd. So how do we prove this? Well, let's let E be H, be the same thing, and then E and X, we'll let that be H prime. Then E confirms H, H prime models H, because E and X obviously entails E, and E and K models H. By the converse consequence condition, then we can get that E confirms H prime. Since H prime is the conjunction of E and X, we know that H prime entails X. So by the special consequence condition, E confirms X as well. For 6.2, assume equivalence, entailment, and disconfirmation duality. So let's remind ourselves what each of these is. The equivalence condition is if you've got a pair of hypotheses, 2 pieces of evidence, and two background knowledge sets of assumptions, and all of them are logically equivalent. The pair of hypotheses are equivalent, the evidence is logically equivalent, the background information is logically equivalent. Then you get confirmation, disconfirmation between E and H relative to K, if and only if you get confirmation, disconfirmation between E prime and H prime relative to K prime. That's the equivalence condition. Entailment is for any consistent E, H, and K, if E and K entails H, but K alone doesn't entail H, then E confirms H relative to K. Finally, disconfirmation duality says this: if and only if E confirms H relative to K, it disconfirms not H relative to K. We're supposed to show that if E and K deductively refutes H, but K doesn't refute H on its own, then E disconfirms H relative to K. So we assume the antecedent, E and K entails not H, and K doesn't entail not H. These two, by the entailment condition, yield confirmation from E to not H, and by disconfirmation duality, disconfirmation of H by E. Show that if H and K deductively refutes E, but K does not refute H on its own, then E disconfirms H relative to K. So again, assume the antecedent. So H and K entails not E, and K doesn't entail not H. Then E entails the negation of H and K. Hence, E and K entails not H. You may need to take a moment to verify that those entailment claims follow, but they do. In any case, once you've verified it, then we can conclude as above that E disconfirms H relative to K. 6.4 says, pick a language. It has n number of objects, n number of constants that refer to objects, and it has just one predicate letter. So at least 2 objects can have as many as you want, finite number. In that case, m dagger for any value for n that you want to pick of being f is going to be 1/2. This is because Carnap likes measures that honor symmetry or honor the principle of indifference. And so I give you a quote from the Titelbaum book about M. Dagger. M. Dagger captures the natural thought that a tautological background should treat each of the available possibilities symmetrically. M. Dagger applies a principle of indifference and assigns each state description the same value. So remember, state descriptions are lines on the big long truth table for the language. And here, if we have n number of constants, you're going to have a whole bunch of lines on the truth table, 2 to the n, because for each object, you have a line where f is true and f is false. And if you treat all of those symmetrically, half of the lines will have an coming out f, and half of them will have an lacking the property f. So you're going to get probability of 1/2. And then the probability distribution dot that we're talking about treats an unconditional probability as a conditional relative to k, where k is going to be tautological background. And that guarantees that the probability of tautologies, all of them, is 1. Evidence E confirms hypothesis H relative to K just in case the conditional probability of H on E exceeds that of H, which is equivalent to the measure telling us that H given E and K exceeds the measure of H given K. Now, we're supposed to show that any non-contradictory proposition K expressible solely in terms of FA1 through FAN minus 1, given any such non-contradictory proposition, the M. Dagger measure on AN being F relative to K is going to be 1/2. Here's how we prove that. We talk about disjunctive normal forms again. And if you remember, the disjunctive normal form of a proposition is just a disjunction of lines on a truth table. All of the lines on the truth table where the formula in question comes out true. So the disjunctive normal form for AN being F starts out with exactly half the lines of the truth table, because half of them will have AN being F and the other half will have AN not being F. Now, any non-contradictory proposition K involving any of the other atomic formulas will rule out exactly as many lines of the truth table that are FAN, FA sub n, and not FA sub n, leaving the percentage of remaining lines split half and half between the two. Since M-Dagger assigns probabilities by the principle of indifference, the M-Dagger measure on FA sub n given K is going to be 1/2. What does the result you demonstrated in part A have to do with Carnap's point that M-Dagger doesn't allow learning from experience? The answer is just that no matter what truth you learn for a specified language, the probability of the target claim of investigation remains unchanged. And I should supplement that. It remains unchanged provided what you learn is consistent with both a claim and its negation. And that's, of course, what learning from experience works like. And when you learn from experience, you take some information which doesn't entail a certain result, but is supposed to probabilistically change your opinion, at least in some cases. And here, no such change in probability ever happens when you learn something that's consistent with both the claim and its negation. So Carnap invented a highly sophisticated way of massively failing to account for how you learn from experience. That's what M-Dagger is. Very fancy, very beautiful, doesn't work at all. 6.5, so make a probability table over state descriptions for the 4 atomic propositions FA, FB, GA, GB. In the right column, enter the values Carnap's M star assigns to each state description. Okay, so 6.5, we're moving from M-Dagger to M star, and so instead of applying a principle of indifference to state descriptions, which is what M-Dagger did, M star assigns them to structure descriptions. So we need to make sure we pay attention to what the structure descriptions are. Structure descriptions are generated from property profiles, and for a language that has just 2 constants and 2 predicate letters, there are going to be 4 property profiles. An object has both of the properties. It has the first but not the second. It has the second but not the first, or it has neither. So there are 4 property profiles. And then for 2 objects, you get the following structure descriptions. Now, let me point out what the parenthetical line number refers to. So if you construct the long truth table in the usual way across these 4 atomic formulas, you get 16 lines. And I have numbered the lines. And for each of the state descriptions, I have said which line satisfies the structure description. So the line numbers are state descriptions. The description is a structure description. And notice there are 10 structure descriptions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4 out of these 10 structure descriptions, there's only one way for them to turn out to be true, because the structure description says both objects are the same in a certain respect. So notice at line 1, both objects have property F and property G. And notice as well at line 16, both objects lack those 2 properties. Note as well that at line 13, there's a reference to the other object being the same. And at line 4, the other object is also the same. All right, so lines 1, 4, 13, and 16 satisfy one structure description all on their own, and no other line satisfies that as well. So both objects can have both F and G, lack both F and G. Both objects can be F but not G, and both objects can be G but not F. The other structure descriptions, there are 2 ways for them to be realized by a line on the truth table. So just take one example. One object has both F and G, and the other has F but not G. Now that gives you 2 places to insert the name of an object. So you can put A as the one that has both F and G, or you can put B as the one that has both F and G. And then you'll put the name of the other object in the second position. That means there are two state descriptions that make that structure description true, lines 2 and 3. And we do the same thing for all of the other structure descriptions. What we do then is we apply the principle of indifference to the structure descriptions. Since there are 10 of them, each structure description has a probability of 0.1. And then when there's more than one way of realizing a structure description, we just split the probability between the various ways in which it occurs. Now, the most there are in this case is 2 ways for a structure description to be realized. So if there's only one way, as in line 1, the M star measure assigns 0.1 to it. But for the second structure description, there's 2 ways for it to be realized, namely lines 2 and 3, the state descriptions at 2 and 3. So we just split the 0.1 probability that M star assigns to that structure description. We split it equally between the 2 ways. So that gives us a truth table that looks like what's on your screen. There are 16 lines, 4 of them have a probability of 0.1. Every other structure description can be realized in 2 different ways. So each of them has a measure of 0.05. And you can verify that that will sum to 1 as it's supposed to. Okay, so that's a probability table of the sort asked for. Now, use your table to show that the M star measure has this probability exceeding this one. All right, now you know that a conditional probability is just a division problem by the ratio formula. So we put this conjoined to the condition itself as the numerator. So we want the probability of FB and FA and GA and GB over the probability of the condition itself. Okay, so what's the measure of FA and FB and GA and GB? Well, that's line 1 on the truth table above. So its probability is 0.1. What's the probability for the condition itself? Well, there's 2 lines on the truth table that have that. I think it's probably going to be maybe lines 1 and 3. Let me look back up there to make sure I'm on the same. Yes, lines 1 and 9. Notice line 9 is the one that has all 3 of them being true. Oops, I'm wrong. FB is the thing on which is conditioned the conjunction of FA, GA, and GB. So line 1 is an FA, GA, GB line. And the other one is line 5, FA, GA, GB. So it has a probability of 0.05, so we sum the 2, we end up with 0.15 in the denominator. So our answer is 2/3. We do the same thing for the other side. Which lines are both FB and FA? Well, that's lines 1, 2, 3, and 4. Sum all of that, you get 0.3 in the numerator. And then you look at all of the FA lines, and we don't even need to add those because you know that on these measures, the principle of indifference, the way it's applied, is going to render every atomic formula, the unconditional probability of it will be 0.5. So we have 0.3 over 0.5, which is 0.6. All right, now use your table to show that this measure is the same as this measure. All right, now the second measure is easy for us to calculate. You know it's going to be 0.5 because it's just an unconditional measure on an atomic formula. This is the one that's a little more complicated. There's one line that realizes the conjunction of all four of those, and it has a probability of 0.05. And there are two lines. Let me use my annotator. There are two lines that realize this condition, FAGA and not GB, and each of them has a probability of 0.05. So our denominator is 0.1. 0.05 divided by 0.01 is 0.5. So the M star measure on those two are the same. Now, problem D asks us to explain how this relates to M star's handling of analogical effects. If you studied in inductive logic before the 20th century, what you would have wanted is for a theory to be developed that allowed inductive generalization and inductive prediction, and also sustained arguments from analogy, because we do this regularly. We argue by analogy for a certain conclusion. Well, M. Dagger didn't do very well with learning from experience of any sort. M star at least does a bit better at learning from experience. So for example, part B shows that if you learn certain things, they can change the probability of a claim. So if all you knew was FA and then you came to learn GA and GB, probability of FB goes up relative to what it was before. So at least some learning from experience can occur by M star. The bad news is you don't get the full range of analogical reasoning that Carnap thought you were supposed to get. In any case, in the first case, more alike cases accrue, leading to a higher overall probability. In the second case, the positive analogy between A and B is countermanded by a negative one. So in the first case, you start out with a very simple analogy. Object A has property F, so maybe B has that property as well. It's not a great argument for it, but it's a probability enhancer, let's suppose. And then suppose you learn that both A and B have another feature in common. That gives you even more reason to conclude that B has property F. Okay, but in the second case, you're looking at the unconditional probability of B. And now you learn some things about object A. First, what you learn is it has a feature in common with B because it's A, but you also learn that they have two other features that they don't share. A has feature G, but B doesn't. So there's a better analogy in the top case than in the second case. And that's reflected in the way the probability enhancement principle gives you confirmation in the top case, but not in the second case. So for 6.6, we're supposed to argue without constructing a probability table for, let's see, 1, 2, 3, 4, 5 different claims. The last claim, let's start at the back and work backwards. The last claim follows from B, C, and D. So the important thing is to be able to prove B, C, and D. And B will require paying attention to how we prove A. But let's start going backwards. First, the unconditional probability of any atomic formula is always going to be 1/2 by Carnap's M star measure, just like it was for his M dagger measure. So that's fine. Just D is just a trivial result of the way in which the principle of indifference works for these two Carnapian measures. Now, C is a little bit harder to see, but we've already proved something like this earlier. After answering question D below, we can generate an answer here by noting the logical independence of the last objects having property G and the evidence that we've got. The evidence leaves open the last object either having or lacking G, so you'll get the same number of structure descriptions available both for this claim and its negation. And that will give us a probability of 1/2 for M star. All right, let's go to A and B. I think A is easier to see, and then B, once we see how A works, we'll see that too. For both sides, we have a conditional probability, and by the ratio formula, that gives us the conjunction of this equivalence claim together with E double prime, and the conjunction of this lack of property G together with the evidence claim, both divided by the same number. So the denominator just drops out of the picture here. So let's ignore that. The only thing we'll think about is the conjunction. The conjunctions of not G, A sub 100 with E double prime and the equivalence claim. So look at the right side first. The conjunction on the right side is satisfied by exactly the lines on the truth table where our final object, A sub 100, lacks both properties, which is exactly the same line that satisfies the equivalence claim on the right side. That equivalence claim comes out true when the last object has both properties or lacks both properties. And the line where it lacks this property is the very same line where they're both lacking. Okay, so you're going to get an equivalence there. Now, how about the equivalence of this same measure on the left side with the opposite one on the right side? Well, there's two ways to see this. One is to look down at our answer to see what's the measure of G with given the evidence, and that will be, turns out, the same as the measure of not G with that property. So given that the not G one is the same in A, we could derive B. But if you don't want to derive it that way, think of it this way. Similarly to the one above, take the left side, the equivalence claim together conjoined to the evidence. There's exactly one line on the truth table that makes the left equivalence true together with the evidence. And there's exactly one, not the same one, but exactly one that makes the right side true. These two lines are symmetrical in terms of the measures given the way structure descriptions are constructed. So the two measures are the same. And then E follows from B, C, and D, and we're done with the problem. We're supposed to show, this is really going to be very easy for the first one, show that the R measure of confirmation violates each of the constraints. So here's what we want. We want the positive degree of confirmation to equal the negative degree of disconfirmation between H and E. So if this is a positive number, it doesn't matter what the number is. Say it's 17. This should be minus 17. If this is 0.2, this should be minus 0.2. All right, now as soon as you see that formula, if you understand how log measures work, you'll see that there's no way that's ever going to happen. I mean, it's not like there's just a random counterexample here. There aren't any cases. Well, actually, there might be cases where both of them have a measure of 0, but that would be it. So the R measure is a logarithm, and the numbers in question range between 0 and 1 inclusive. So the log of 0 is negative infinity, and then it climbs all the way from negative infinity up to 0. So every ratio measure is going to be a negative number, except in the case where the probabilities are 1, and then it'll be 0. So pick any example you want. Here's one. Let H be rolling a 2 on a fair die and E be rolling an even number on a fair die. Then the ratios turn out to be negative 0.477 for the confirmation claim and negative 0.176 for the disconfirmation claim. Okay, so that was very simple to show that it violates hypothesis symmetry. Logicality is a bit more tricky. The counterexamples aren't quite as easy to come up with. Anyway, logicality is this claim. All entailments receive the same degree of confirmation and have a higher degree of confirmation than any non-entailing confirmations. All right, so here's a trivial counterexample to it. Let the probability of the hypothesis be 0 and pick some E that entails something with a probability of 0. Then R is undefined. So you violated the first conjunct of logicality. All right, that's a little bit tricky, a counterexample. Maybe it's trivial. So here's a more substantive one. Take a 10-ticket lottery and let the hypothesis be my ticket loses, and let the evidence be tickets 1 through 10 all lose, where the lottery in question is a 10-ticket lottery. Then the probability of my ticket losing is 1, but E doesn't by itself entail H. Now, the reason it doesn't entail it is a bit tricky. So tickets 1 through 10 all lose tells you that the probability that your ticket loses in a 10-ticket lottery is 1. The probability is 1, but the evidence by itself doesn't entail that your ticket loses. It only entails it together with the claim that there are exactly 10 tickets in the lottery. So E alone doesn't entail that your ticket loses, though it does together with the information that this is a 10-ticket lottery with tickets numbered 1 through 10. Okay, yet R gives every probability of 1 the same confirming power. So logicality is violated in 2 different ways.